In this problem, we're asked to find h of j omega if its magnitude characteristic is as shown below. So if we look, we start off at minus 10 dB, and when we get to omega equal 5, the curve turns up at 20 dB per decade, which must indicate the presence of a simple 0 at omega equal 5. Then at omega equal 12, the slope becomes 0, so we must have a pole at omega equal 12. At omega equal 25, the curve turns down at minus 20 dB per decade, and then at 40, it turns to minus 40 dB per decade, so they must both be poles at 25, omega equal 25 and omega equal 40. So then, h of j omega, then it's going to be some constant k0. Our 0 is at omega equal 5, so we have j omega over 5 plus 1. Okay, that would account for this slope going to plus 20 dB per decade. Then we said, well, the slope goes to 0 at omega equal 12, so there must be a simple pole at omega equal 12. So we get j omega over 12 plus 1. Here the slope goes to minus 20 dB per decade, so there must be a simple pole at omega equal 25. So we have j omega over 25 plus 1. And then the slope at omega equal 40 goes from minus 20 to minus 40. So we must have a simple pole at omega equal 40, so we have j omega over 40 plus 1. And the only thing left to do is find out a value for k0. So if we look, the gain down here at these lower frequencies is minus 10. So minus 10 dB is equal to 20 log base 10 of k0. So we have minus 0.5 is equal to the log base 10 of k0. If we solve for k0, then that's 0.3162. We substitute that in, that'll give us our expression for h of j omega.